All right, guys, so we're doing chapter 4, just trying to do a few extra problems to help you guys out for your practicing. So again, I've got a worksheet. If you look at the first two, maybe take a picture. There's a couple of reactions. And again, when we write reactions, that sometimes will be step 1 of a process where we're gonna set up a reaction, but then have to do math from it. Need to be pretty efficient and pretty accurate as you set up these reactions. So the first one says we're doing an aqueous reaction of magnesium acetate and ammonium carbonate. Now, it doesn't give the physical state with each compound, but it says it's an aqueous reaction. So to me, that means that both compounds are going to be mixed in aqueous form. And then once they react, we may or may not have something that comes out of the aqueous solution, either as a precipitate or as a gas. So we'll see. Anyway, so magnesium acetate, you have to know magnesium is +2, acetate is -1. So pretty quickly, it's got to be Mg, and then the acetate, CH3COO. You're going to need 2 of those. That's aqueous. Plus ammonium carbonate. NH4 is +1. Carbonate's -2. So I'm going to need 2 ammoniums. Again, that's aqueous. When they react, I know that it's going to swap partners. Magnesium's going to end up with carbonate. That's +2 -2. So it's just going to be MgCO3. I don't really care how many there were on the reactant side. I'll balance that later. But then I also am going to make the ammonium with the acetate. So that's going to be NH4, CH3COO. And that one gets to be 1-to-1 because they're both +1 -1. Okay, so now the next thing I need to look at my physical states of my products. Doesn't matter what my reactant physical states were. Since there's an aqueous solution, I just want to know whether these are going to be soluble or not. Carbonates are mostly insoluble except for group 1 metals and ammonium. So this is going to be a precipitate. It's going to be a solid. And then ammonium, the rule is anything with ammonium is always soluble. Same rule applies to acetates. So this is probably an extremely soluble compound. It's going to be aqueous. Okay. Then I can balance the equation. And notice that I kind of look at it instead of element by element. In a double displacement reaction, you can look at polyatomic ions. There's 2 acetates over here. So I'm going to need 2 acetates over here. So I'm going to put a 2 in front. That also gives me 2 ammoniums to match up with my 2 ammoniums here. And then I have 1 carbonate, 1 carbonate, 1 magnesium, 1 magnesium. So really that 2 right there is the only thing I had to do to balance the equation. Again, you got to get through that quickly, and that's it. All right. The next reaction I mentioned was the reaction of solid sodium bicarbonate with aqueous sulfuric acid. So sodium bicarbonate is NaHCO3, solid, plus sulfuric acid is one of the acids you're supposed to know, H2SO4, aqueous, that was all given, yields. Now, again, double displacement. Now this time, the hydrogen and the bicarbonate or hydrogen carbonate are going to go together. Basically, HCO3 minus has a -1 charge. So I'm going to put 1 hydrogen on there to make it neutral. That's going to make H2CO3 plus, and then sodium goes with sulfate, Na with SO4. I know that sodium is +1, sulfate is -2, so I need Na2SO4. Then I think of physical states. A key here, you may have noticed in the beginning I have a carbonate and I have an acid. Anytime I react a carbonate and an acid, I'm always going to make carbonic acid. I can recognize it beforehand, or when I make H2CO3, if you recognize that that's carbonic acid, we talked in the lab and in previous lectures, this compound is unstable. If you have carbonic acid in solution, it will break apart into water and CO2. So you can erase it, you can mark it out, whatever you want to do. It needs to be H2O and CO2. Those are the actual products I end up with. H2O is the liquid, CO2 is the gas, and then my sodium sulfate Group 1 metals are always soluble, so that's going to be aqueous. So actually my products end up being those things right there. Again, you don't have to circle it. You could have erased the carbonic acid if you want, but I end up with 3 products from this reaction instead of 2 like I normally do with double displacement reactions. Okay, so that's it for that. Now I'm going to move to my third problem. So the third problem is the one that's the paragraph. So take a look or take a picture. All right, so I've got a solution, a water sample that has barium in it. The solution is 100 milliliters, but then it says I take a 10 milliliter aliquot. Okay, now aliquot means I take part of it out from the rest, and then that part is what I actually do my experiment on. So the 10 milliliters is what I'm going to actually utilize in my calculations. So I take the barium solution, I add sodium chromate, and it's going to form a precipitate. Now, the barium in solution, they're going to be barium ions, okay? Metals in solution have to have a charge in order to be dissolved. Neutral metals don't dissolve in water, okay? So this is going to be barium ions, Ba plus 2, aqueous ions in solution, and then I'm going to add sodium chromate. Okay, now chromate's minus 2, sodium's plus 1, so it has to be Na2CrO4. Now, when I look at that, and that's going to be aqueous, I'm going to add sodium chromate specifically with the intention of getting all the barium to precipitate, because the barium and the chromate are going to be insoluble with each other. So the sodium is actually just a spectator. If I did the net ionic equation, split these apart, basically the barium ions that were in the sample and the chromate ions that I've added, they're going to come together to form barium chromate solid. And then the 2 sodium ions are just going to be floating around. They're not really doing anything important, okay? But the formation of that precipitate, that's what it's talking about. It says you add sodium chromate, and then the precipitate is dried and weighed, and the mass is 0.025 grams. So that's 0.025 grams of that compound. So I'm going to start with 0.025 grams of BaCrO4. And then I have to find the molarity, the concentration is the molarity of barium. Okay, now what do I need to do? I need to have the molecular weight of barium chromate, so I'm going to divide by the molecular weight, which I don't actually know what it is right now. I'm going to divide by the molecular weight to get the moles. That's going to be 1 mole to the molecular weight in grams. Once I have the moles of the barium chromate, well, it's 1 barium chromate to 1 barium ion. So essentially, the moles of barium chromate and the moles of the barium ions are going to be the same. Then, if I have the moles, the molarity is supposed to be the moles per liter. All that I need to do in the last step, I have moles on top already. I'm actually just going to divide by the liters of solution. Now this is where they gave me 2 volumes in the beginning of the problem, but I actually did the experiment with 10 milliliters. So my volume, if I divide by 1,000, is going to be 0.01 liters. So if I follow my units, first step, divide by grams, the grams cancel, gives me the moles of barium chromate. Then I use the 1-to-1 ratio to get the moles of barium. And then I have the moles. If I divide by the volume, that gives me the molarity. Okay, so the only thing I'm lacking in this setup, I should know what the molecular weight of barium chromate is. It would have been nice if I had added that up before I made the video, but I didn't. So you get the molecular weight there. do the calculation, and then that answer will be your molarity of the ions. Okay, so I'm going to cut off, and we'll have one more video for chapter 4 after this.